Welcome to Demystified TV, where technology meets simplicity. I am your host Mridul, and in each episode, we break down the latest tech trends, gadgets, and innovations into bite-sized, easy-to-understand pieces. Whether you are a tech enthusiast or just looking to stay ahead in digital world, we have got you covered. Get ready to demystify technology and make it work for you. Let's dive in. Why making microchips is so complicated? The story of VLSI. Today we are exploring the journey of microchip creation, focusing on VLSI, very large-scale integration. In today's episode, we will go over stages of VLSI design, including managing technical challenges, the role of different players, tools, and languages, quality control, and even final stage called tapeout. Plus, we will cover post-silicon validation, a crucial step that helps ensure that these chips work as intended in real-world conditions. Let's dive in. To start, what exactly is VLSI? VLSI, or very large-scale integration, is the technology that allows us to place billions of transistors on a single microchip. Each of these transistors is like a microscopic switch, turning on and off the process information. Imagine trying to fit billions of light switches onto something as small as your fingernail. That's essentially what VLSI does, and it's why this technology is so essential. It let us create powerful, compact, and energy-efficient devices from phones and laptops to smart appliances. So why is VLSI so complex? It's because designers have to navigate multiple technical challenges. Three major hurdles, including managing power, controlling timing, and ensuring clean signals. When you pack billions of transistors into a chip, they all need power. But with so many transistors switching on and off, they can generate a lot of heat. Engineers have to make sure the chip stays cool while still operating efficiently. To do this, they use techniques like clock gating to turn off unused sections of the chip, reducing power consumption and heat. They also use power gating to completely disconnect inactive sections from the power supply. But designing these mechanisms to work flawlessly is no small task. Every tiny adjustment affects the overall power and heat. Next, timing control. A chip's transistors are like symphony orchestra, with each transistor needing to perform in sync with the others. If signals arrive too early or too late, the entire chip can malfunction. Engineers use timing analysis tools to make sure signals arrive at each part of the chip precisely when needed. They also use buffers and adjust connection lengths to keep timing in check. This is incredibly meticulous work since they are dealing with nanoseconds, a billionth of a second. The third challenge is signal integrity, which is all about making sure the signals between transistors don't interfere with one another. With billions of transistors so close together, signals can overlap, leading to a problem called crosstalk. To fix this, engineers place shields between sensitive connections and use specialized routing to minimize interference. They run complex simulations to identify potential issues and make adjustments until they find the best layout. Imagine placing soundproof walls in a noisy room to make sure everyone can hear each other clearly. It's a similar concept. Creating a chip isn't the job of just one company. It's a collaborative effort involving several players, each with a critical role. Design companies create the digital blueprint of the chip. They use specialized software known as EDA, that is electronic design automation tools from the companies like Cadence, Synopsys, and Mentor Graphics. These tools help simulate the chip's behavior and test the design. Once the design is ready, it's sent to a semiconductor foundry like TSMC or Intel, which manufactures the actual chip. A key part of this collaboration is the process design kit, or PT PDK. The PDK is essentially a handbook the foundry provides to the design company. It contains all the manufacturing rules, guidelines, and technical specifications, making sure that the design aligns with the foundry's capabilities. It's like getting the blueprint for building of a complex car in a factory with unique assembly lines. If the foundry upgrades its necessary process, it updates the PDK, and the design team may need to make adjustments to fit the new standards. The chip design process is typically divided into front-end and back-end design. Front-end design is where the core logic is created. Engineers use programming languages like Verilog and VHDL to describe the chip's functionality. Think of it as creating the brain of the chip, defining what each transistor will do, how they will all work together. They run simulations to verify that chip's functions work as planned. It's like writing a script for a play, detailing every move, every line, every interaction. Once the front-end work is done, we move to the back-end design, which focuses on physical layout. Engineers take digital logic and map it onto the physical chip, placing each transistor and wire in the right spot. This stage is where the engineers face layout challenges. They have to consider size, power, timing, and signal interference. They route connections carefully, balancing constraints to create compact yet efficient design. It's like designing a city map with roads, buildings, and utilities all within very limited space. After the design is complete, the chip goes through rigorous testing and validation to ensure it will work as expected in real-world conditions. First, engineers conduct simulations to test the chip's functionality under different conditions. They do functional verification, making sure each part of the chip performs as intended, and timing verification, checking that signals arriving precisely on time. There's also formal verification where engineers use mathematical proofs to ensure that certain properties are upheld. This is crucial for avoiding bugs, as fixing errors in later stages is costly and time-consuming. Once the design passes all the simulations, the foundry manufactures a prototype and we move to the post-silicon validation. This stage involves testing a physical prototype of the chip in real-world conditions. Engineers run it through stress tests, checking how it performs under different temperature, voltages, and workloads. Post-silicon validation is essential because simulation, while powerful, can't always capture every real-world variable. Think of this stage as a dress rehearsal where the chip gets a final test to catch any unexpected issues. Any bugs or performance problems identified here have to be addressed quickly because we are nearing full production. This stage ensures the chip won't have any major surprises when deployed in devices that people use every day by conforming to the chip's reliability and robustness. Post-silicon validation is the final safeguard before the design is locked in for mass production. After passing all the design and validation stages, we reach at the tapeout stage. Tapeout is when the finalized design is sent to the foundry for production. It's the no turning back point, like hitting the send of an email. After tapeout, any changes would require a complete redesign, which would mean months of delay and significant costs. For smaller companies, there's also option using multi-project wafers or MPWs. Using multi-project wafers or MPWs, these allows several designs to share space on a single silicon wafer, which lowers production cost. It's like renting out a small booth at a fair rather than booking the entire venue. MPWs are valuable option for companies after tapeout needing only a limited quantity of chips. After tapeout, the foundry manufactures the chips, but the journey isn't over yet. The chips go through packaging to protect them and manage heat, ensuring they can handle real-world conditions. They are also tested one final time before being shipped off to the companies that integrate them into devices like phone, computers, and cars. And that's it. From start to finish, the journey of a microchip involves a dizzying number of steps, challenges, and key players. Today we explored the complexities of VLSI, including technical challenges in power, timing, and signal integrity, the roles of PDKs, EDA tools, and foundries, the essential quality checks in verification and post-silicon validation, the final steps of tapeout and production. I hope you enjoyed today's deep dive into the world of microchip design. Stay tuned for more insights into the technology that power our lives.